In this chapter, we'll talk about the reactions that is happening at the alpha carbon of carbonyl compounds. We'll first talk about the acidity of alpha hydrogen. So far, in all the reactions of carbonyl compounds, we have been focusing on the functional group, carbonyl group, where the nucleophile goes and attacks this carbonyl carbon and thrusts these electrons onto oxygen to form a tetrahedral intermediate. From there, either a nucleophilic addition product or nucleophilic addition elimination product will be formed depending upon the basicity of the incoming nucleophile. But carbonyl compounds can also have second site of reactivity, and that is the alpha hydrogen. Now, what is alpha hydrogen? Alpha hydrogen is the hydrogen that is connected to the alpha carbon. When you take the functional group, so here is a functional group. This carbon right here is the alpha carbon. And any hydrogen that is attached to the alpha carbon is called as the alpha hydrogen. Let's say if the R is going to be a methyl group here, okay? So these hydrogens right here are also alpha hydrogens. When you compare the electronegativities of carbon and hydrogen, they are about the same, because of which the bond between carbon and hydrogen is going to be strong because they are formed by mutual sharing of electrons. This is especially true in the case of ethane, where you can see that this carbon is sp3 hybridized, and the hydrogens that are connected to this sp3 carbon cannot be easily removed. But this is not the case with respect to carbonyl compounds. In carbonyl compounds, the alpha hydrogen is relatively acidic. For example, when you take the case of aldehydes or ketones, so this is an aldehyde, this is a ketone, the pK value of this acidic hydrogen is going to be roughly around 16 to 20. In the case of esters, it's going to be around 25. So these compounds which have an acidic hydrogen is bonded to the sp3 carbon are called as carbon acids. Here are some examples for our carbon acids and their pK values. It is now important to know why this alpha hydrogen is relatively acidic. Let's take the case of ethane. Let's say that we remove this hydrogen from ethane molecule. Then the electrons that is left behind is going to go onto this carbon. So the conjugate base is going to look something like this, where these electrons right here are localized. But in the case of carbonyl compounds, since you have an adjacent carbonyl group, the electrons that is left behind when this hydrogen is removed will be delocalized. Let's say that you have a base comes and abstracts this proton, because of which these electrons right here that is left behind is going to go and form a bond, form a double bond, and the carbon-oxygen double bond is going to break and it's going to move on to oxygen. Now here, because the electrons are delocalized, the conjugate base is stabilized. There are two important stabilization effects between these two conjugate bases. First is this structure right here doesn't have any resonance contributor, but this one has. And the second thing is that the negative charge is on the most electronegative oxygen atom. But here it's present on the carbon. So because of these two reasons, we can definitely say that this conjugate base is stabilized, and because of which this acid that it had started from should be relatively strong. So this is relatively strong. And this is weak acid, strong acid, and this is a weak acid. When we were talking earlier, we have said that the aldehydes and ketones are going to have a pK value between 16 and 20, whereas in the case of ester, it's about 25. Now, what is the reason why esters are less acidic than aldehydes and ketones? Now let's see what's going to happen to the conjugate base. Let's say that you're going to remove this hydrogen, that's going to result in this conjugate base. But in this conjugate base, there is going to be two effects, okay, two competing effects. In this structure, we have got two atoms which have got electrons on it. Okay, both the oxygen and as well as the carbon, they have got electrons on it, and both of them have the ability to delocalize those electrons onto oxygen. So when the carbon pushes these electrons, it's going to form one resonance contributor. And when the oxygen pushes those electrons, it's going to form the other resonance contributor. And because both of these pairs of electrons are competing for delocalization onto the same oxygen, the acidity of this hydrogen is greatly reduced. And that is the reason why you have a higher pKa value for ester. Apart from carbonyl compounds, there are also other compounds which can have an acidic hydrogen, acidic alpha hydrogen. So here are some examples. We have nitro compounds which have a pK value of about 8. In the case of nitroethane, it's about 8.6. And nitriles, the pK is about 26. For N-dimethyl acetamide, it's about 30. And in each one of these cases, when these hydrogens are pulled, the electrons will be delocalized onto an electronegative atom. Whenever you have a CH2 group that is flanked by two carbonyl groups, in that case, the acidity of the alpha hydrogen is going to be greatly increased. Let's now take a look into this compound, 2,4-pentane-dione. This is a diketone, and it's more specifically called as beta diketone. Why? Because if you consider one of these functional group, okay, so this carbon right here is an alpha position with respect to this functional group, and this is a beta carbon. And because you have two keto groups which are beta with respect to each other, this is going to be called as beta diketone. Now in this compound, this hydrogen is greatly acidic. Why? Because it's going to have two resonance contributors for the conjugate base. Let's take a look into this. So let's say you're going to pull the hydrogen from here. When you pull the hydrogen, it's going to form the conjugate base. And here is the conjugate base. Now these electrons right here can be delocalized onto this oxygen to give one resonance contributor. At the same time, they can also get delocalized onto this oxygen. So accordingly, we'll be having two resonance contributors. Let's say that it's going to get delocalized onto this oxygen. Then here is the resonance contributor for it. If it's going to get delocalized on the other side, then this will be the resonance contributor for it. And because it has got two resonance contributors, it is relatively stable, and because of which the acid that it had started from should be strong. Here is one more example. This is an example for a beta keto ester. Here there are two functional groups. Here you have a keto functional group and also an ester functional group. This part right here is an ester. Now with respect to the ester functional group, the keto group is in the beta position. So this carbon right here is an alpha position, and this one is a beta position. Therefore, this is an example for beta keto ester. Here also this hydrogen right here is acidic because the electrons that will be left behind can be delocalized on to both of these oxygens, giving rise to two resonance contributors.